Okay, fast approaching the end of the semester, like 2 days from now. Today, I want to remind you that your either or lab is due today. Any late work, homework, labs, makeup tests, extra credit, all that stuff needs to be in by 3:10 on Friday, which gives you an extra 15 minutes. You're welcome. Today we're going to talk about empirical and molecular formulas. We're going to introduce a plane crash activity with a couple of examples. Here is your extra credit opportunities. I'm not going to spend a lot of time talking about this. It's all on the website. So that's linked right through your Canvas homepage. So go to that. It's on the left-hand side. There's a little link for extra credit. If you need it, want it, there it is. Let's just cut and paste it. All right, so we're going to start with what we already know how to do. We're going to do one example of percent composition just to refresh your memory about stuff you already know. Then we're going to transition from determining the percent composition of a substance to determining the empirical formulas and the molecular formulas. And at this point, you may not know what an empirical formula is, but you will very soon. We'll get to that in just a moment. So, on the front side of your sheet, there's not, I suppose from your perspective there's a lot of notes, but I feel like it's not a lot of heavy-duty material today. So you already know how to find the percent composition of MgCO3. You already know how to name MgCO3, magnesium carbonate. So we're going to use a periodic table to do that. Periodic table, you'll find the mass of magnesium. 1 mole is the atomic mass, 24.31 grams, plus 12.01 grams for 1 carbon. And of course there's 3 oxygens, so we're going to take the atomic mass of oxygen and multiply it times 3 to give us 48. And when we add those all up, 84.32 grams is the total mass of magnesium carbonate. So when we want to find the percent composition of magnesium, what do we do with those numbers? Find the percent of anything, we divide what by what? Jack? Part by the whole. So for magnesium, we're going to take our 24.31 divided by the total mass. And we find that we've got almost 29% of the mass of this compound is magnesium. And you certainly don't need to wait for me to click buttons to do this. You already know how to do it. The next one we're going to do is our carbon. Earlier in the year, when we were doing this, we did a lot more rounding. In this unit, we're going to ask and encourage you to use more significant figures in your calculations, just so that we end up with better results. So rather than using 12, use 12.1 or 12.01, I should say. And then for oxygen, you see that more than half of the mass of magnesium carbonate is from oxygen. And of course, when we add all these up, since it's the percentages of the whole is 100% of the whole thing. So all these percentages should add up to 100. If you're keeping several digits, using several significant figures in your calculations, you're going to end up with 100, or at least much closer to 100 than you will if you're doing a lot of rounding. But even if you're doing a little rounding, your result should still add up to 99.8 or 100.1, 100.2, something like that. So that you know you did it right. If you add these all up and you get 74.6, you messed up. Okay, so that's what we already know how to do, just a quick review, and we'll be using that again. We've got two types of formulas we're going to talk about today, empirical formulas and molecular formulas. The first one is the empirical formula. The empirical formula it's still a chemical formula, like what we've been working with for the last couple of months, but it's always going to be reduced down as much as possible. So we know water, for example, is H2O. Hydrogen peroxide is H2O2. The empirical formula for water is going to be H2O because we can't reduce that down anymore. But hydrogen peroxide, there's two hydrogens and two oxygens. We could reduce that down. It's a 1-to-1 ratio. So the empirical formula for hydrogen peroxide would simply be HO. And we'll give you a couple of examples so you see that. The molecular formula is the actual ratio, the actual number of each element in the compound. So in one molecule of hydrogen peroxide, there actually are two hydrogens and two oxygens. The empirical and the covalent formulas can be the same, but they certainly aren't always the same. So one way to express that is to say that the molecular formula is equal to the empirical formula multiplied by some integer, n. N can be 1, could be 2, could be 3, but it's not going to be 1.5 or a fraction or a decimal. So here's a simple example. Molecular formula of this compound is C6H6. Clearly we can see that there's 6 of each in there, so we can factor out the 6 and we get CH in parentheses with a 6 outside, where the 6 is your N value. So our empirical formula is not the CH with a 6 outside the parentheses. The empirical formula is just the CH. If we're talking about ionic compounds, metals and nonmetals, or polyatomic ions, they're always going to be given as the empirical formulas. Sodium chloride, NaCl, is a 1-to-1 ratio, MgCl2. Aluminum sulfate, there's going to be 3 sulfate ions for every 2 aluminum ions. Can't simplify that down anymore and keep whole numbers in there. Same with potassium carbonate. So ionic formulas are always given as empirical. If I'm going too fast, let me know. As I said, our molecular formulas may or may not be empirical, or they may or may not match the empirical formula. So here's a couple of examples. Already mentioned H2O. We can't simplify that down because if we cut our hydrogen in half, then we end up with half of an oxygen. So we always want whole numbers. So we got a 2 and a 1 there. So the empirical and molecular formula for water, or H2O, is the same. For this compound, we got 6 carbons, 12 hydrogens, 6 oxygens. What would be the empirical formula for this guy? CH2O. Everything there can be divided by 6. And so that's how we reduce it down as much as possible. Perfect. "12 carbons, 22 hydrogens, 11 oxygens." That 11 kind of throws a little wrench in the works. So if it was at least an even number, we could divide everything by 2. But our 22 and 11 are divisible by 11, but not 12. So that guy's stuck, and it's going to be the same. Okay? That's easy so far, correct? Anything dicey to this point? All right. So how are we going to figure out what the empirical formulas are? It's basically a 3-step process. You can summarize this as much as you would like. When we're given the percent composition of a compound, we are told that it's 12% carbon and 26% oxygen and 42% nitrogen or whatever. All those percentages add up to 100. So we're going to assume that we're starting with 100 grams of whatever substance we're given. So whenever you're given a percent of something, you're going to assume you have that many grams of that. Typically there's going to be at least 2, if not 3 or 4 different elements in that compound. So we're going to convert each of those values of grams into moles. The smallest of those values we're going to divide into the other values that we got. And if you're not 100% comfortable with what I'm telling you, we're going to walk through an example step by step, so you'll see these steps in action. We're going to take that smallest number of moles and divide it into all of our other values, including the smallest number of moles. So whichever is our smallest number of moles, when we divide it by itself, that's going to give us 1. Everything else is going to be something bigger than 1. Might be 1.5, might be 2, might be 2.25, whatever. We're going to have a bunch of numbers. That's going to be the ratio. But we want to get those into whole numbers. And so we look at those values and figure out, okay, what number can we multiply them all by to get them into whole numbers? And that result is going to give you the subscripts for your empirical formula. Are we good to go? So close. So close. All right, so let's do this example together. Shows adipic acid. I'm guessing that most of you have never even heard of adipic acid and certainly don't know what the formula for adipic acid is. But it does have 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen. So our first assumption is that all 3 of those numbers are going to add up to 100%. We set of percentages, we're going to replace the percents with grams. So we're going to start with 49.32 grams of carbon, 43.84 grams of oxygen, and 6.85 grams of hydrogen. And we're going to convert each of those into moles. As I mentioned in the last class, there are a number of steps to this process, but they're all steps that we've done. We're just putting a few steps together to get us, allow us to do something we haven't done before. But these are all simple steps. So to find moles of carbon, we're going to take our mass of carbon and multiply it by moles per gram. 12.01 for carbon, 16 grams per mole for oxygen, and 1.01 grams per mole for hydrogen. Now, I've tried to leave a little space to the right of your T-chart so that you can just take the results of your T-chart and do steps 2 and 3. So you can kind of continue on with that T-chart. It's technically not going to be a T-chart anymore. So we just completed step 1, converting all of our masses to moles. Step 2. Divide by the smallest. Well, our smallest one is 2.74 moles of oxygen. So we're going to divide everything by 2.74. So our 4.107 moles of carbon divided by 2.74. We do the same with hydrogen. And we do the same with oxygen. As I said, the smallest one divided by itself is always going to be 1. Everything else is going to be something bigger than that. Of course, it is possible you might have 2 numbers of moles that are both the smallest. That's fine, that's not a problem. Still going to use the same process. So now, we've got, what this is telling us is that for every 1 mole of oxygen, or for every 1 atom of oxygen, we have got 1.5 atoms of carbon, 2.5 atoms of hydrogen. So in our formulas, we can't have halves, so we just got to find some number to multiply these by so that they all end up being whole numbers. Well, clearly, if you've got something, halves of something, you can multiply by 2, you'll get whole numbers. If you've got something in thirds, multiply by 3, you get it into a whole number. Got something in fourths, 3/4 of something, you multiply it by 4 to get it into a whole number. So these are the only fractions we're dealing with here are halves. So we're going to multiply everything by 2. So we take our carbon times 2, that gives us 3. And our hydrogen, 2.5 times 2 gives us 5. And 1 times 2 obviously gives us 2. I'll refer back to that previous screen where the answer ended up being 2.47. If you use more significant figures in your calculation, those numbers are going to become more and more like 2.5 or 2.67, whatever the case might be. So you got to interpret your answers a little bit, but a lot of times you're going to get something that is, say, 3.99. Just don't get your uglies and bunnies, just recognize that's really close to 4, it's 4. Okay, so this set of numbers are the subscripts for our empirical formula. This tells us that for every 2 oxygens, we've got 3 carbons and 5 hydrogens. So that is the smallest whole number ratio of atoms for that particular compound. Giddy up? Any questions? Okay. Our last step is simply to find out if the empirical formula and the molecular formula are the same. So on the right side of the sheet is the second half of the problem. It tells us that the actual molecular mass of this compound is 146 grams per mole. If the mass of the compound that we just came up with a formula for, our empirical formula is 146 grams per mole also, then they're the same. If our empirical formula is smaller than our molecular mass, then we've got to figure out how much smaller so that we can figure out how much we need to increase the subscripts of our empirical formula. So the formula mass we just came up with was C3H5O2. So the first thing we want to do is find the molecular, or the molar mass of that empirical formula to see if it matches up with 146. So when we do that, we got 3 times 12 plus 5 times 1 plus 2 times 16, and it adds up to 73. '73 and 146, they're not the same. So how do they compare to each other? You probably do this in your head, but you're going to recognize that it's 1/2. So this next slide is simply going to tell you what to do to figure out that it's 1/2. So we're going to divide the actual mass by our empirical mass. And that's going to tell us how many times bigger the actual mass is. So 146 divided by 73, 2. That tells us that the actual adipic acid is twice as big, twice as massive as the empirical formula that we just came up with. So that means we need twice as much of everything. So we're simply going to take our empirical formula and multiply it by that ratio, 2. And C3H5O2 becomes C6H10O4. Everybody agree that's quite a few little steps? And hopefully you all agree those are all easy little steps. Just kind of get used to walking that path, and this becomes just a very simple process. Not sure if this was, how many of you even have current events anymore, but this may have been discussed in your current events class this morning. Plane crash. It's very sad. still academically purposeful for us.
Put a name on it.
Two more?
Oh. Backwards.
Here's hoping none of you had any friends or relatives on Mole Airlines flight 10,231.
Wait a second.
Here's some live footage.
Oh, that's what cars have.
Yeah. So I feel it'd be prudent just to take and have a moment of silence in memory of the victims on Mole Airlines flight 10,231. Thank you. Okay, while we get ready to talk about this assignment is due next semester, which means that your tour may or may not be your tour.
Oh, no.
Uh-huh. So if you would like to take a moment to check your schedule, find out who your tour is next semester, so that you're not turning it into...
Is it Monday class? Monday class.
Yep, Monday class. Could still be the same guy. Bless you. Bless you.
Just Exhibit A.
No, I wanted that there.
All right. Why are you girls all smiles back? All right. So, being wise in the ways of empirical formulas, percent composition, and molecular formulas, like you are, you're being asked to help solve the mystery of Mole Airlines Flight 10,231. Because the suspicion is that somebody was murdered and they had an accomplice and somebody bombed the airplane. Frickers.
Using substance.
So, we're going to walk you through this, do a couple of examples for you. Your task, I'm sure you all recognize Joe Friday from Dragnet. Here he is. Your task is to solve for the formula and name of each of the drugs identified on the posting notice. So for example, passenger A was determined to have some unknown substance in his or her blood. Percent composition is given there for you. We got to figure out what substance that was I determine the formula, and then referring back to the clipboard of possible compounds found on the scene. Once you've done that for each of your notes, for each of your sticky notes, then you're going to refer to the list of victims. They all have a short little bio. Suspected drug dealers, an environmental engineer, and blah, blah, blah. You want to connect those passengers with your Post-it notes, so you can say that, Johnny Majors was passenger A, or that Cadillac Jackson was passenger F, or whatever the case might be. Using only the evidence found on the scene, just the facts, ma'am. And once you've identified who is who, I don't know, which person corresponds to which Post-it note, then you're going to fill in the summary on the bottom of that front sheet, which will identify who was the murder victim, who was the murderer, along with their accomplice, and who bombed the plane with what formula for this compound. So the first thing we do is convert our percentages into grams, and then convert those masses into moles. Significant figures is going to be a big deal here for you to get good results. So please look at how many significant figures you have given in your compound data and use the same number of significant figures from the periodic table for your molar conversions. So here we got 4 significant figures in 67.31. So we're going to use 12.01 with 4 significant figures, as opposed to 12.011 or whatever comes after that. So that is grams of carbon for every 1 mole of carbon. Little pluggage and chuggage, that gives you 5.6045. When you're calculating the number of moles, don't get too tight with your extra digits. So it's better to keep more digits than to round too much. So we do the same thing with hydrogen. 1 mole of hydrogen, we got 3 sig figs here, so we're going to go 1.01. 3 sig figs there, and that gives me 6.911. Moles of carbon, moles of hydrogen, nitrogen, 3 significant figures, so that becomes 14.0 grams of nitrogen for 1 mole of nitrogen. 0.3298. And finally, oxygen. Four significant figures. The oxygen is 15.999. I don't know how many nines there are, but to keep that as 4 significant figures, that's going to become 16.00. So we got our moles for each element. Identify what our smallest is. and divide everything by the smallest. I'm not exactly sure what your calculator gives you, and you're welcome to tell me, but I know that when I did this one, it wasn't exactly 17, but it was like 16.99 or something like that. So it's pretty much 17. Unless you're off by, I would say, a tenth or more. Probably more than that. You can assume that it's going to be that whole number. This one was 21. This one's 4. So they're already in all whole numbers. We don't have any decimals, fractions, so all we need to do is write this out. We've got C17, H21, NO4.
Cocaine. Cocaine.
There's one.
Alec Jackson.
Maybe. Maybe. I wouldn't make any assumptions until you have completed all of your Post-it notes. Kind of put all those pieces together. Shall we do one more? Or is... Yes, sir. I'm sorry. Who wants me to do another one? Okay. Only takes one, Lex. Only takes one. Look, next one's cocaine too. No, really. Not really. All right, so this is the second of the 2 passenger B Post-its. And this one I don't have all my calculations written down for, but we're going to get rid of our percentages, replace them with grams, convert to moles. And I think once you get rolling, you're going to find that this goes fairly quickly because you're going to be using all the same elements, so you're not going to have to be referring to your periodic table very often. Bless you. So 46.66 divided by 12.01 is 3.885. 4.48 divided by 1.01, 4.4356. 31.1 divided by 14.0, 2.22. 17.76 divided by 16. Is 1.11, which is our smallest. We're going to divide everything by 1.11. All right, so you'll see here that two of these numbers didn't come out exact. Obviously, 1.11 divided by itself is 1. 3.885 divided by 1.11 is 3.5. That's nice and clean. The other ones are off by, again, just like 100th or a little bit. So 3.996 is 4. 2.0012 is 2. But we still have that 3.5. We need to have them all in whole numbers. So we simply multiply by 2 to get rid of our halves. We're going to do that for everything. So this time we got C7, H8, N4O2. So when you look on your clipboard, you'll find thiobromine is the chocolate flave. This is the third one, not the second one.
Oh.
Yeah. We skipped one, but we skipped the first one. Okay. That's pretty nice, huh? I got one more slide for you then. So this assignment has an extra credit opportunity associated with it if you choose to pursue that. So if you'd like to earn some extra credit with this assignment, you can do a little additional investigative research and discover the story behind the story, or you just make up your own. So 1-page minimum. What are some of the details that weren't known to the public that you have discovered or created? Your story needs to be original, should be creative, should not be handwritten, so please word process and print, and hopefully it'll have some humor in it. That'll make it more fun for us to read and more fun for you to write. Humor is not a prerequisite, but